All right, welcome back. So in this video, we will be doing an introduction to interest formulas. So we're still looking at exponential growth and decay. Okay, we're still looking at exponential functions here. We're still looking at exponential growth and decay, but now we're going to be putting them in word problems, and we'll be looking at them using interest, decay, population growth, bacteria growth, things like that. Okay, so go ahead, pause the video, try the first two on your own. It is just a warm-up of graphing two functions. All right, let's see how you did here. So the first one was exponential decay. Here I have the parent points. Here's the rule for this. Here are the new points based on the rule. Same idea for the other one. Parent points, rule, new points. Okay, and then there's your domain, range, and asymptote. All right, let's move on to the new info. So for everything that you're doing today, you will need a calculator. This unit has a no calculator and calculator part of your test. Everything that we're doing right now would be found on the calculator version. So I'm going to go ahead and pull up my calculator so I have it ready available, but hopefully not taking up too much room. All right, there we go. Okay. So what we're talking about today still is exponential growth and decay, but we're talking about exponential growth and decay interest formulas. You can model growth or decay by a constant percent increase or decrease with the following formulas. So you will need to know these formulas. At first, it can be a little daunting to look and be like, what? I got to know 4 formulas? But they are all adaptations of the first one, okay? So we're going to look at that. So we have, this is exponential growth. So we're talking about growth here. This is the simple interest formula. We have A equals P times the quantity of 1 plus R to the T power. So A, what does that stand for? The final amount in the account. So let's just pretend this is talking about a bank account. So like that is how much money you have in the account after the calculation. P is called the principal, which is just the initial amount or the amount that was invested into the account. So that's the starting amount. R is R right here is our rate, and it's written as a decimal. So since this is the growth formula, that's plus R. Notice in the decay formula, it's minus R. So that's the only difference between the growth and decay formula. Always written as a decimal, and that is for the year. So this is for when that there is, you would use these formulas when it is just for 1 year. And then there is no N in this formula. I'll get to that in a second. And T is the time usually in years, okay? So if this was bacteria growth and they were talking about minutes, then it could work for that too, okay? But we use a different formula for bacteria growth, so we actually know. All right, next we have this formula. So that was growth and decay. So that's a simple interest formula. Once again, the amount is equal to the principal times 1 plus or minus the rate to the T power. Next we have if it is the interest is compounded. So you could have interest compounded monthly, daily, quarterly, whatever, okay? So if it is compounded quarterly, which is 4 times per year, we are going to divide our rate by 4 and multiply our time by 4. If it is compounded monthly, we would divide our rate by 12 and multiply our time by 12. If it is compounded daily, then we would divide our rate by 365 and multiply our time by 365. So notice it is the same formula as this one, except we are dividing our rate and multiplying our time by that compounding. All right, lastly, we have compounded continuously formula. So we'll get more into this at the end of the lesson, but if there is compounding continuously, which I'll explain at the end of the lesson, then we are using what's called the PERT formula. So it's still A equals P, which is the principal, and then instead of using 1 plus R to the T power, we use E to the rate times time power, lovingly referred to as the PERT formula because it looks like the made-up word PERT. It's P times E to the RT. Okay, let's go ahead and get started. So we have, 5 different problems here, okay? And making sure we're putting them in the calculator correctly is part of this, okay? So this says, upon graduation from Glenbard North, you receive an inheritance of $10,000 from a rich relative. Must be nice. That you didn't even know existed. The money has been placed into a certificate of deposit, which is also called a CD, which earns 6% interest compounded annually. So compounded annually is just once, so really it's not compounded. We just say it's 6% interest annually. What is the value of the certificate in 6 years? So once again, even though you see compounded in there, it says annually. That's 1 time per year. We do not need to divide by 1. Let me get back to my pointer. We don't need to divide by 1 and multiply 1, right? So we can just use this formula right here. Okay. So let's go ahead and write our equation. Notice it says equation, so you need to have an equal sign in all of these. Okay, so we have amount is equal to. So we need our initial amount, which was the $10,000, times 1 plus, this is earning interest, so it's plus. Our rate, which is 6%, so that's 0.06. And then to our time power, which is 6 years. All right, now we have to go ahead and put this into our calculator, okay? So we are going to do 10,000. This one's easy to put in your calculator, parentheses. You could either add those two and write one number, but I'm not going to. I'm just going to write 1 plus 0.06, but you could have just write 1.06, because that's what 1 plus 0.06 is. And then to the 6th power, hit enter. This is money, so we are rounding to the nearest cent. $14,185.19. Okay? Looking at this over here, it's 19 with a 1 next to it. If it was 19 with a 7 next to it, we would have put 20 cents. Okay, next it says, suppose that instead of compounding the money annually, the CD was compounded quarterly. What would the value of the CD be in the 6th year? So very similar formula, but we have to divide that rate by 4. Was it quarterly? Yes. So this is n equals 4 here, all right? And we have to multiply the year by 4. So we are going to write our equation, A equals 10,000 times 1 plus, we are going to do 0.06 divided by 4, and then to the 4 times 6 power. So something important. When we're putting this in our calculator, we have to make sure that it is doing orders of operations or not doing orders of operations. Yes, well, we wanted to divide this first and then add 1 to it. We wanted to multiply these two numbers and not bring this to the 4th power and then multiply the answer by 6. So what we're going to do when we put this in our calculator is we're going to make sure that there's another set of parentheses around that, and we are going to put 24 here when we put it in our calculator. Okay, so 10,000 and then parentheses, 1 plus another set of parentheses, 0.06 divided by 4, close the red parentheses, close the blue parentheses to the 24th power. Hit enter. And the reason I could put 4 times 6 up there, but some calculators don't have this. They have a caret, and then you have to put in parentheses 4 times 6. So that's why we're saving ourselves that commotion there. Okay, so we would then have $14,295.03. Not 2 cents, because it rounds up to 3. All right, let's talk about the difference in these answers. Compounding quarterly is better. You have more money, right? $100 and almost $10 more by compounding quarterly, right? So what's happening here is that the interest is taken 4 times a year instead of once a year, and therefore you are making interest on money you already got that you made in interest, right? So like, oh, I made this much money in interest, but now I'm making interest on that interest, which that's confusing English, but yes. So if you look at this, compounded monthly should be even better. Compounded daily should be awesome, okay? All right, so obviously this is not going to be a much difficult task here. A equals 10,000. Let me make sure. Now suppose the CD is compounded monthly. What would the value be at the end of the 6th year? So same thing, right? 1 plus 0.06 divided by 12, and then 12 times 6. So we're gonna change, or we're gonna put this in parentheses, and then we'll change this to 72. 72. Excuse me. Okay, so 10,000, parentheses, 1 plus, parentheses, 0.06 divided by 12, close parentheses, to the 72nd power. Once again, I could put 12 times 6 in my calculator. It's not a big deal. All right, $14,320.44. Now, I haven't tested in a few years what happens if I don't do that double set of parentheses. So let's actually find out what happens so that we can actually experience that together. 1 plus 0.06 divided by 12 to the 72nd power. And I get $14,320.44, the exact same answer. So for this particular problem, it has proved my theory wrong because it is it's doing orders of operations. It's dividing the 0.06 divided by 12 first, all right? And then it's adding 1. So it is doing orders of operations. So I guess you don't need the 8,000 parentheses, but I do them for when they get more complicated in the future. Trust me, I've experienced terrible things. I know I sound like a liar right now. Okay. Next, right here, we have A equals, let's read it. Compounded daily, assume 365 days per year, so no leap year. Write the function to determine the CD's value at the end of the 6th year. So same idea, 10,000. 1 plus 6% still, divided by 365. And then times 365 times 6 years. Okay, so 365 times 6, 2190. So I'm going to do 2190 instead and put that in parentheses. Trust me, I know that it messes up somehow somewhere in the future. It just wasn't here because it is doing orders of operations. Plus parentheses 0.06 divided by 365, close, to the 2190. Enter. All right, $14,332. So not that big of a difference as it was from no compounding at all. 14,332 and 87 cents. So I was mincing my words here, but not that big of a difference from here to here. There's only a $12-ish difference, okay? But if you compared compounding every day to only compounding once a year, I'd much rather have the extra 100 and some bucks, right? Okay, so that covers basically, remember, it's just an intro, most of the compounding, but then we have this question. What if your parents had deposited some money in a CD when you were born so that they could give you $10,000 upon graduation? How much money would they have had deposited, assuming that the interest rate all these years had been 6% compounded annually? Okay, so let's go ahead and figure this out. So I was looking at, the final amount that they wanted to give you was $10,000. We want to know how much money that they would have to deposit and then compound it annually. So 1 plus our rate, which is 0.06. We don't have to divide by 1 and bring to the first power. And then how many years has it been since I was born? 18 lovely years. All right, so now I want to solve for A. I could put this in my calculator and see what it is, but I don't necessarily care. So I'm just going to say, all right, this is multiplication here. To get A by itself, I'm going to divide both sides by that amount. So I'm going to put in my calculator 10,000 divided by 1 plus 0.06 to the 18th. All right, now I tend to work backwards when doing these because once again, I don't want to worry about all those sets of parentheses that I have to do. So I'm going to do 1 plus 0.06, which is this. You could use the plus sign or not, to the 18th power. And then I hit enter, and I get that crazy funky number, which I'm not going to write down because it goes on much longer than that, and I don't know where it stops. But then I have to do 10,000 divided by that. So you can, if you have a calculator to grab it. If not, you can hit second answer. Enter. And we have 3503.44. So they would have had to invest $3,503.44 into the bank account when you were born in order to give you $10,000 when you turned 18. Okay. And a CD having an interest rate of 6% is possible as of right now with our economy. Savings account, it's a little high for a savings account, but for a CD, completely possible. So keep that in mind. Okay. Last thing we're going to talk about is this last formula, the compounded continuously. And what the heck is E? Okay, so E is Euler's number. In this previous activity that we had, an example was presented of how interest could be compounded monthly, yearly, annually, and quarterly we did. This process is important because there are many examples of exponential growth in nature that compound. Continuous growth can be in bacteria, populations, radioactive decay, and many more examples. However, these examples do not compound yearly or quarterly. They grow continuously, right? So like cancer cells grow continuously. Radioactive decay, so carbon removing itself from an object that is dead continuously. Population growth, continuously. Continuous growth means that the object is constantly compounding, not once a year or 4 times a year or 12 times a year or every day. One way to think of this relationship is that the interest is earning interest. And I already mentioned that. The interest is earning interest. It says, in the early 1700s, a Swiss mathematician, Leonard Euler, discovered this value to be an irrational constant with the value 2.7182 ... so on and so forth. It is irrational. It goes on forever, ever. There's 2 places in your calculator that you can locate E. If you hit the second button and then the divided by, that's just E, and it'll give you that 2.7182812228, so on. I just read it wrong, but you know what I mean. And it goes on just like pi forever and ever and ever. Another place that you can find it is if you hit the second button and then the LN button, that's 3 up from the bottom on the left-hand side, right there, it'll give you e to a power. So this way, if you have to put in a power like we do, it's already setting you up so you don't have to use the caret. But if I put e to the first power, it'll show you that 2.718281828, right? Okay. So I get a little bit off track there. So it says, recall that continuous growth happens constantly, which represents, I missed this. Euler used the letter E to refer to the constant, and it is known as Euler's number. So just like when we want to use pi, we use the pi button in our calculator. We don't type in 3.14 or any decimal approximation. When we want to use E, we're going to type in the E button. Okay, we're not going to type in 2.71828. All right, so keep going here. Recall the continuous growth happens constantly, which represents compounding with finite frequency. Use the function f of x equals, I'm going to skip past using the decimal, e to the x to model continuous growth. So here's PERT once again to remind us what the variables stand for. A is our final amount of the growth or decay. P is the starting amount, the initial amount, the principal. Okay, E is that base, which is a constant. It is, instead of using 1 plus or 1 minus something, okay? It's the base of E, which is the button in our calculator that we'll use that represents the number 2.71828, ... R is our rate of growth written as a decimal or decay. And then T is the number of time periods, often years, okay? We're using this formula when we were doing a problem about bacteria growth or decay, population growth or decrease, or radioactive decay. So we just have one example and then we'll do some more tomorrow. This says the growth rate of human population is approximately 1.1%. If the world population is 7.888 billion, what will the population be in 5 billion years, right? Sorry, 5 years in billions, not 5 billion years. What will the population be in 5 years? In billions. All right, so let's write our equation, okay? So we have A equals, or Y equals, right? So we need that final amount, right? which we are looking for, right? We're looking for the final amount. So I'm going to do A equals. And if you did Y equals, nobody cares. Okay, A equals. And then I need my initial amount. So the amount that I'm talking about right now is 7.888. And I'm not going to put a bunch of zeros on it to turn it into billions. I'll just put the word billions on my answer. And then since this is population growth, I'm using E, so that was P, initial amount, E to the rate times time, PERT. So my rate is 1.1% written as a decimal, so that's 0.011, times my rate, which is 5 years. See that? Okay, and if you want to put these in parentheses so you can actually see them, you can. All right, so we're going to do 7.888 E to the, so I'm going to use second ln, and then 0.011 times 5. Enter. And then remember our answers in billions. So we have 8.334 billion people. Okay? All right, that's it for today. Why don't you go try some homework, and then we'll pick back up tomorrow and try some more.